So welcome back everyone to the next topic. All right, so we come back to this method to actually derive the relationship between the variables. So there are two methods, right? The first method is the Rayleigh's method, and then second one is the Buckingham pi theorem. Okay, this is the second one. So we look into this second method on how to derive the equation, okay, or the relationship. So yeah, I think from the term itself, all right, you can see here Buckingham pi. So the pi, the use of this symbol pi to actually derive an equation is something like the previous second example, right, from the Rayleigh's method. But that one is actually we only have one group, right, one group of dependent variables, right? Okay. So this time we will have more than one group. So meaning there are several pi. Okay. So the question is actually when to use the Rayleigh's method and when to use this Buckingham pi theorem, right? So usually for Buckingham pi, we use this when we have more than four variables, right? You can see in our two examples previously. So the first one we have the period of the pendulum. If you still remember that one we have total four variables, including the dependent variables, right? And the second one is the one on the go back, all right? The second one, which is this one. This is, yeah, this is a combination, right? Wherein the dependent variables is not, the dependent variable is not stated here, all right? It's just asking us to combine these four variables, independent variable, the torque, discharge, the diameter, and the density. Total, we have four here, right? So you can see this one, there is also no dependent variables mentioned, okay? But we just need to combine all these. So the total number of the variables you can see here is four, all right? And therefore, with this, you can do the solving the equation through the exponent, concept of the exponent, wherein we try to work based on the dimensional homogeneity concept, wherein we try to equal the sign of the exponent value to the one on the left. All right, so that's basically the idea from the Rayleigh's method. Okay, so let's look at the second method now, which is the Buckingham pi theorem. Right, so for this, the theorem that states if we have a physically meaningful equation, all right, so it's nothing here. If let's say we have an equation, all right, and then we have number of physical variables, this is the n, okay, this is the one that I mentioned just now, the four, the total number, all right, okay, for example, this is the first number, the n number of variables, okay. And then the second one, we have K. So K is the number of independent fundamental physical quantity. We know what is fundamental physical quantities or fundamental dimensions, right? The seven, right? Just the total, we have seven fundamental, but usually in this application, to derive relationship, we use these three only, right? Mass, length, time, MLT. So usually the number of K is equal to 3. All right, just take note what is N, what is K. All right, K is the number of fundamentals. So usually, as in a Rayleigh's method, whatever physical variables that we have, all right, we try to expand this in terms of the fundamental physical quantities, yeah, in terms of fundamental dimensions, right? For example, the diameter is equal to capital L, which is length, right? And then viscosity is equal to, derive this is equal to, you need to derive this one. If you're not struggle to expand this one is Pascal second, right? Then density, this one is very more common. This one is mass over volume. right? So it'll be equal to big M over L cube, right? Something like that. So we usually, the first step is the same like before. We always try to expand these variables in terms of the fundamental quantities, okay? And then we know what is N, and then the K is just a number of the fundamental physical quantity used. So in this case, usually number is 3, right? So then original equation is equivalent to this resulted expression, okay? So in the previous example, we actually only have, all right, in the previous one, we only have actually one, right? Dimensionless group, which is the pi, only one, right? Okay, but this time, because the number of variables increasing, okay, so we use this one to actually identify the total number of dimensional groups. Okay, so basically the number of dimensional group, there will be several pi. So pi 1, pi 2, pi 3, and so on. All right, so the number of pi group will be equal to this n minus the k. Okay, right? So don't worry, we'll look at example. So in mathematical forms, we have a physical meaningful equation such as, all right, you know this, whereas Q1 is the dependent variable. Okay, this is a function sign and all the independent variable, all right? We can also write it in this way, where we will put everything in here, including the dependent variables, and just put it equal to 0 sign. Okay, so where Q is equal to N physical variables, right, expressed in terms of K independent physical unit. So N is the number of physical variables, right? And K is the number of the fundamental dimensions, right? Independent physical units. Okay, so let's look at some further explanation. So K equal to 2 if there are two fundamental physical unit dimension. Okay, this is what I mean by K. All right, you can have actually capital K, right, to be consistent with the previous slide. All right, so K will be equal to 3 if there are three fundamental physical unit. So K is the fundamental. So, right, we'll look into this later. So the equation can be restated as this. All right, so you can take note that instead of the variables now, we have the dimensional group, pi 1, pi 2, all right, and so on. So this is actually a dimensional. So it becoming a new variables, right? But it's actually may contain more than one uh, variables from the original problems. Okay, all right. So pi is dimensionless parameter constructed from the variables q. So it's a new one. It's a new parameters, something that is being lumped together, right, to simplify the the relationship, okay, development. All right. So let's look at the example here. Let's say you have this, all right. This is a flow of fluid in a pipe, all right. So determine the set of dimensionless group that represent the relationship between, let's say this is the purpose, all right. You want to determine the set of dimensionless group. So the question is set is how many group is possible from here. So this is question, all right. So you can have this, a flow of fluid inside the pipe, all right. So you have several parameters or variables. D, the diameter of the pipe. This is the viscosity. This is density of the fluid. This is epsilon, which is we call it surface roughness. Surface roughness, the dimension is just length, right? Capital L, all right? And then we have a length of pipe, all right? And then we have P1, P2. This is the force, driving force, or the pressure, okay? And then we Q, which is the discharge, and V is the velocity, okay? Right? So all of these parameters, now we have a lot. How many we actually have? 1, 2, 3, 4, 5, 6, 7, 8. We have 8. So obviously we don't use Rayleigh's method for this because it's very complicated. It's not possible to do this, all right, because the number of variables is too big, all right, all right. So let's try to identify the variables, right, listed given in the diagram here. So to see that whether they fall into which group. So flow properties of an incompressible fluid in pipeline. Flow properties. So this is flow properties. Flow properties, and then we have properties of fluid, and then we have dimension of pipeline, driving force for the moving fluid. All right, driving force is easy, just P1 and P2. All right, the difference. Dimensions of pipeline, this one is very straightforward. This one we have a length of pipe, diameter, surface roughness, right? Property of fluid, property will be the viscosity, the density, right? And the flow properties, these will be these two, okay? It's something like that. So imagine in a real world case wherein you just have to identify all of these parameters by yourself, right? Imagine that situation, okay? But don't worry, for our case, usually all of the things are given, and we just need to come up with the dimensionless group. All right. So when it comes to dimensional group, of course, the question is how many dimensionless group, okay, is possible, okay, uh, of all of the variables uh, even, okay. And then the second one is what are the exact dimensionless group, okay. So two things. All right. Let's look at this one. Identify the important step one, the important variables in the system. So yeah, we have done this. Okay. In terms of flow rate is which one? Okay. So this is Q, the formula for Q. All right. Okay, we have driving force. I think we have done this. Part dimension. Okay. This one is just to organize things so that we don't miss any of the variables, right? And to ensure that they falls under these categories. Okay. All right. So first step done. We have identified the uh, variables. Okay. But of course, as usual, right? When you identify the variables, you should know what are the variables, the breakdown of the variables, because later you will need to express the variables in terms of the fundamental variables. Okay, you still have to do that. Okay, all right. So you do this, list all the variables and their dimensions. Yeah, dimension means the fundamental dimensions. So yeah, we have all the variables here. We just list out, and then we try to expand each of the variables to include the fundamental dimensions. Okay, so this is velocity. Velocity is to be equal to length over time, right? This is pressure, right? So pressure is equal to force divided with area. Hope you're familiar with that by this point. Okay, pressure and force, you should know the difference, something that you should remember, I think, because these are quite common. All right, and then we have diameter, right? Diameter, length. So we try to express all of these variables in terms of the fundamental variables. Okay, so just now we have the parameter of n and k. So this is what it means. Okay, number of variables, all the variables stated. So just sum them up, right? So equal to 7, and then dimensions. Oh yeah. So how many types of dimensions? So K is actually the type of the how many type of dimensions. So there are 3 because we are using MLT throughout here. Okay. So we have 7 and 3 here. So the pi, right? You can write it out this way, but you can also, I think better you should use the symbol pi. All right. So now the pi is actually the number of dimensionless group possible. So it'll be equal to 7 minus 3, there'll be 4. So meaning we can generate four uh, dimensionless group, right? So in other words, we can reduce the number of original problem variables from 7 to 4. So basically simplify the work. Okay. So next question is how to generate this group based on Buckingham Pi theorem. So step 3, choose a set of reference variables. All right. If for Buckingham Pi theorem, we have these reference variables. Reference variable. Okay. Reference variables. So the original variables, we say problem variables, right? Variables given in the problem. So we say problem variables. So this one we say reference variables. So for the reference variable, right, the criteria are it must satisfy these following criteria. Number of variables must be equal to the minimum number of fundamental dimensions. So this is we have 7 and we need to choose the reference variables. Okay, so we know that the k is equal to 3, right? Because we have this MLT. All right, so the number of variables should be equal to the minimum number of fundamental dimensions. So in this case, 3. Yeah, all right. Number of a reference variable, 3, because we have 3, right? Usually the reference are 3, okay? Okay, the second one, no two variables have the exact same dimension, okay? Okay, when we choose the 3 reference variable, they must have different dimension, okay? All right, we see this later what it means. And then the third one, all the dimensions that appears in the problem variables must also appear somewhere in the dimensions of the reference variable. So let's say we choose the 3 new reference variable, right? Later I'll show you how to choose this one. So all of the fundamental dimensions that's present from the reference variable should have all the dimensions that appear in the problem variables. This is actually fundamental variables. So maybe a little bit confusing at this point. So don't worry. Later you can come back to this and understand each of the step. All right. So we need to look at the real example to really understand this. Okay, let's go here. So yeah, now we need to choose 3 reference variables, right? So what is actually a reference variable? So yeah, choose the ones with simple combination of dimensions, because in total we have 7, right? We have 7. So these 3, this is the pipe properties, right? The pipe properties, right? Okay, and then we have this one another 3, and then this one we have another 2. This is in total we have 7 variables. So of the 7, we need to choose 3 reference variables. Okay, why 3? Because we have 3 fundamental dimension use. Okay, because we need something to represent L, T, and M. Okay, all right. So for L, so which variables contain L? Okay, if you go back here, well, we need the 3 reference variable, because later the 3 variables we need to express them in terms of LMT. I mean 3 different equation. Okay, so all right. So of all of these, which one contains the L? All right. So of the 7, you can identify here which one contain L. You can have all of these containing L, right? But choose the simple one. All right. So maybe this one, D is equal to L or L equal to L, right? This is length of pipe, diameter of pipe. This is surface roughness. So this one is a simple one because it's straightforward. L will be equal to D. So of these 3, which one to choose? You can choose this one, all right, D. You can also choose this one, L will be equal to L, all right? So yeah, you can make your choice. So Based on this, all right, the example given, all right, they choose D, all right, the D. Okay, why D? All right, because it's simple, all right, and then D is equal to L. Yeah, if you express it in terms of the dimension, okay, fundamental dimension. Okay, let's move to the second fundamental dimensions, time. So go back to the table. Which one of the seven contains time? You have this one, right? You have this one, you have this one. So, and then the next question, which one is the simplest one? The simplest one will be this one, right? Because it's just length over t, right? Just two variables, two dimension. Okay, so we take this one. Velocity is equal to length over time. This will be the one that we should choose. Okay, let's come back here. All right. Yeah, so these are all the variables containing time, but we choose velocity. Okay, loss because it's simple. All right. Okay, we have covered length, we covered time, and then the third one, the mass. All right. For the mass of the seven, these two contains the fundamental dimension of mass. All right, so which one to choose? Viscosity, of course, a bit more complicated. All right, so we better choose the rho, which is density, which is equal to mass over volume. So we try to expand this one, right? So we get this. So this is what it means by to generate the three reference variables. What it means by reference variable, meaning the original variables from the problem, all right, but we try to expand it to contain the fundamental variables, and then we need to make this as the dependent variables in the equation. That's the reason why. So length, time, and mass. We pick these three. Okay, so done. Three reference variables. And then step 4, as I said before, all right, we need to rearrange the three reference variables, all right, uh, wherein the fundamental variable is now becoming the dependent variable, right, in such form. We know that diameter of the pipe is equal to length, so we need to put it like length equal to the diameter. All right, so same for all of this, right? The second one we choose because of the t, right, the time. So this time we need to make the t as the dependent variable here, all right, in this equation. All right, okay, and then everything if you take note here, right, this one, let's say originally containing the length. This is a fundamental variables. Okay, so we need to change the fundamental variables to the one that contain the problem variables. Like, you know, the L is now becoming the D, right? So we change L to D. Okay, same thing for the rho, right? We have this, so pick this because of the mass. So now we need to put mass as the function. Okay, all right, and the same thing here. Now we have length. Length is the fundamental dimensions. So we need to replace it with D. Okay, now we have this. So step 3, to identify the reference variable, right? And step 4, to actually put the fundamental dimension as the function, also dependent variable. Okay. And then step 5, write the dimensional equation for each of the remaining variables. All right, we have the remaining one. Just now, originally, the number of n is 7. All right, sorry, the number of n is 7. Okay, and then the number of pi is 3, right, because of these 3 reference variable. So we have the remaining 4. Right, for the remaining 4, substitute the result in step 4 for the dimension in terms of the reference variable. So basically these are the remaining 4. All right, so we need to express the 4 in terms of these three. Okay, the blue one. Okay, so this is what we do. Remaining four, from the step 4, we have these three reference variable. And then the remaining 4 variable, we have this with epsilon. This is the length of the pipe. This is the viscosity. This is the force, right? The driving force. So similarly, we try to expand it to contain the fundamental dimensions. And then after that, we use the one that we obtain from step 4, right? Substitute into the equation, and then we have the final form this way, right? So we have a 4 final equation, all right? So for example, the epsilon now is becoming D, all right? The length of the pipe is becoming D, diameter, all right? Diameter of it, because remember, the purpose of this is to obtain a dimensionless group, right? This is the purpose, right? Because, if this one is in the dimension of the right surface roughness in the dimension of L, the D also contains the fundamental dimension is also L. So if you take this one divided with this one, you'll be dimensionless, right? It's the same with this one. This is the trick. For all these 4, you'll be the same, all right? So it means for this one, viscosity, if you take this viscosity, all right, you divide with this one, all right, you'll be dimensionless. Or the other way around, if you take the one on the right side, all right, divided with the one on the left side, you will get a dimensionless term, because that is the purpose, is to produce, to generate the dimensionless groups. So now we have 4 dimensionless groups, okay? All right, step 6. These equations are each dimensional identical. These equations are each dimensional identical, of course, on the left and right, if you compare, right? This equation, right? 1, 2, 3, 4, the blue one. So dividing one side by the other will produce a dimensionless group for each. Yeah, so as I explained to you already, you just divide it, right? One side by the other. Okay, let's say the first one, this one is pi, or this is epsilon over D. Okay, take this one, epsilon divided with D. That'll be, the next one will be the length of pipe divided with D, right? Length of pipe divided with D, and then the rest will be the same. And therefore, of 7 problem variables, we managed to reduce it to 4 dimensionless group. So this one would be simplify. It would be simplifying the whole relationship, right? All of the variables, the relationship between all of the variables. Okay, so that is basically the technique, right? As usual, whenever you get the expression, you try to see whether they are correct or not, right? This is part of the dimensional analysis. So try to expand it to contain the fundamental dimensions, and then you can see that they are actually dimensionless, right? All of it, all of them. Okay. So that's actually the purpose. Okay. So dimensionless variable, if you want to determine the driving force required to transport a fluid at a given rate through pipe, okay, the relationship could be, right, could be written in such way, all right? So let's say if you want to do this, okay, determine the driving force required to transport a fluid. So you go back to the one that you have here, all right, and all of it, all right? You try to identify which one will contain the driving force. So we have group 1, 2, 3, 4. The fourth one contains the driving force variables, right? Okay. Okay, so this is pi 4. All right. So if you need to write the relationship, you write it this way. Okay. You take the pi 4 one, is equal to F and the rest of the the rest of the function. Okay, so then you need to replace the pi symbol with this uh, real dimensions of variables. Okay, the real variables here. All right. Okay, so that was the first example. Okay, so the difference with Rayleigh's method is actually the Rayleigh's method is simple. Usually we just do Rayleigh's method if we have 4 or less than 4. All right. And then it's actually based on the exponent, right? Dimensional homogeneity, the left, the power on the left, on the values of the powers on the left and on the right should be equal. And then we try to solve what are the values of exponent and then replace the values to the original equation. That's how we work for Rayleigh's method. Right, for Buckingham pi, the trick is actually through reference variables. Right, you need to select the reference variables. Usually, the number is equal to 3 because we always use MLT, mass length time. Okay, and then we try to rearrange that one and put it back into the remaining variable. So that's basically how to do the Buckingham pi. All right, so let's look at the second example. The following is a list of relevant parameters that are related to the operation of a pump. Okay, so usually all these things are given. All right. So yeah, but of course, when they are given, you should be able to expand each of the variables in terms of the fundamental dimension. So that can be tricky if you have weird parameters and something that you are not very familiar with. All right, so let's say rho, you know what is rho density, diameter. This one is rotation speed. Rotation speed is per hour. Yeah, this one is maybe you're not very familiar, right? Volume flow rate. Okay, this is Q is equal to volume over time. All right, it's not velocity, right? It's a volume, right? Then we have kinematic viscosity. This is different with the previous the viscosity that we encountered previously, because the previous one is actually absolute, we call dynamic viscosity. So this is kinematics viscosity, is different. All right, take note of this. All right, okay. All right, and then we have power. All right, power, and this is the dimension. Okay, try to remember all these new parameters. Okay, and then we have this is probably yeah, the weirdest one. All right, this is G multiply with the pressure head. So you know what is G? This is the acceleration by gravity, right? You know this from F equal to ma, or W equal to mg. All right, and multiply with pressure head. Pressure head is the unit, is actually this, in the dimension is actually L, right? So you should be able to get this. So yeah, maybe try to find a way to remember these new variables. Okay, but of course I think you should know by this point force, pressure, viscosity, right? Velocity. So these are the basic one. Okay. Okay, so the question is, we need to develop, all right, the dimensionless group. So as I said, the question is how many dimensionless group possible, and then the secondly, what are the dimensionless uh, expression. Okay, so same thing, the step one. All right, so we have n minus k. This one will be number of dimensions group possible. The pi means the number of dimensions group possible. We can have 4 here. All right, and then the fundamental dimensions, we usually have these 3 mlt. All right, so we need to choose the reference variables. Right, how do we choose this one? Of course, we pick the easy one, right? The easy one. Okay, you can check this one. So for length, all right, which one to choose? Of course, The easier one, diameter, right? Because only one dimension. All right, time, right? Rotation speed, because it's only, yeah, same, only one dimension. Okay. And then the one that containing mass, we have which one to choose. We don't repeat with those that have been chosen, right? Mass, of course, we have this one and we have this one. So of these two, which one is easier? Of course, it's this one, and we are also more familiar with this one. There's a reason why we choose rho. Okay, so reference variables, done. Next step is rearrange of this, all right, trying to make the fundamental variable as the function, okay, as a dependent variable, all right. And then everything here, the rest of the fundamental variable, we try to express it in terms of the problem variable as well, right? Like this, t instead of t now becoming, no, it's like this, the L1, right? So instead of L, we use the D, okay? All right, step 4 done. Step 5, okay, substitute, replace it and rearrange, okay? And therefore we have this, okay? The equation will be Q equal to this, and then in order to produce a dimensionless term, we just divide one by the other, right? So in this case, it's Q divided with this. We can also take this divided with Q, right? As long as we can produce dimensionless group, because that is the purpose, right? So we have 4 equations. So we have this way. We have these 4. Okay. So how many number of dimensionless group? We have 4, right? The pi. Okay. So done. That's how we do the Buckingham pi theorem. Yeah, of course, yeah, you need to try, you need to practice, and should not, I mean, you will remember the step if you do more practice, and try to pick the difference, the difference, what are the difference between the two Rayleigh's and Buckingham method, and try to understand their main concept. Then I think it should be fine. Okay. All right, and then we have dimensionless number. Dimensionless number is actually a dimensionless expression, all right? So as I explained to you previously, something that I mentioned, Reynolds number, this is actually one example, is probably the most famous one. Okay, so what is dimensionless number? Dimensionless number are widely applied in mechanical and process engineering. So the numbers are basically developed by engineer, right? Such a number is typically defined as product. This is an example, product or ratio of quantities, all right? Which do have units in such a way that all units cancel out, because it's ratio, right? Ratio, same thing when you divide something with some similar things. So you get dimensionless. So a dimensionless number has the same value regardless of the measurement units used to calculate it. It has the same value whether by metric system or by the imperial system. So this is what it means. Okay, so yeah, again, if we try to revisit why we have dimensionless, right? Because we want to reduce the number of variables. So this one, another reason is because it simplify the relationship, all right? And it's also something that is very well defined by the engineer. So we look to this, all right? So these are some of the example of the dimensionless number, okay? This one established already by the engineers, all right? But of course, at this point, you don't have to remember all this, okay? You will see all this dimensionless number again in the later topics, all right? For example, this one Reynolds number is the one that is used in the fluid mechanics topic. Yeah, mass transfer, we have Knudsen number, right? And then all these heat under the heat transfer. This is a fluid mechanic Becklet number, right? This one also in fluid mechanics topic, all right? And also, yeah, the other one, okay? We have drag coefficient just now. If you remember, in our first illustration, first example on why the justification on having dimensional analysis, right, to reduce the number of problem variables. All right, so we have drag coefficient, if you remember this. Okay, so this is dimensionless. Okay, okay, all right. So this one they are developed by the engineers, all right, and then it's basically very well defined. For example, this one Reynolds number. Okay, this one, let's say if the number is less than 2000, all right, it is said that the system is in laminar flow, right? If it's below 4000, it said the system is under a turbulent flow. So something like that is very well defined number, right? So don't worry, later you'll see what this one in more detail, but the purpose of this topic is actually to show us the technique of to, to derive the dimensionless uh, relationship, right, to between all of the variables. So this is the main thing.